Hello everyone and welcome to another session of DARSim simulator tutorial series. This video number 6 is about ADM or Algebraic Dynamic Multilevel runs for homogeneous and heterogeneous together with fractures and non-fractured test cases. If you have not watched the previous videos, please go and have a look at them as you need those informations as prerequisite for using these test cases and having the runs in this video. In the following test cases, we use SPE10 top layer model with a modified length of 216 meters and a modified width of 54 meters. We discretize the system to 216 times 54, in total 11,600-ish grid cells. We use quarter of 5 spot as well pattern with an injection well at the bottom left corner and a production well at the top right corner. We inject with 500 bar, produce with 100 bar, and we simulate a two-phase water flooding. I want you to go to the DARSim examples repository in GitLab, go to multiscale course, there's a folder called ADM two-phase flow, and when you go in it, you see two folders, homogeneous, heterogeneous. I want you to download the content of these folders using the download button here. If you go in them, you see three files in the homogeneous test case, which is the main simulation input file is immiscible.txt, simulator settings.txt is the other simulation input file, and you have a fracture file. If you go back and go to the heterogeneous test case folder, you see four files. One extra file for the permeability map of SPE10 top layer. Now I have already downloaded these folders. Now we want to go and see the settings and the configurations inside these files. Please open the immiscible.txt, the main input simulation file. Now there's not much that has changed compared to the previous test cases that we have run with SPE10 top layer geometry. So this is the dimension in X and Y and Z in meters, the number of grid cells that we are discretizing, a homogeneous permeability. In this case, we are using a homogeneous permeability of 10 millidarcy across the entire domain. The fluid properties has not changed compared to the previous time. The initial pressure, and at the end, the well patterns. One well as injection in the bottom left corner and one production well at the top right corner. Now we want to run a non-fractured case for now, so keep the fractured off as the keyword, and obviously the name of the fracture file will be ignored when you set it to be off. Save this file, and we go now to the simulator settings. Number of reports is set to be 100. The minimum and maximum size of the time step size is 1 and 30 days. The settings of the fully implicit and linearization using the residual norms, and also the number of the maximum number of iteration has not changed. For the linearized system, we use the MATLAB /operator as the direct solver. Now there are new settings that are involved here. First keyword that it's new, it's ADM, short for Algebraic Dynamic Multilevel method. You have this ADM in capital letters. You set this to be 1, so it's active. For now, ignore DLGR, keep it at 0. We are going to use 2 levels of coarsening. So levels is set to be 2, and the coarsening ratio for every coarsening level is 3/3. So every 3/3 fine scale grid cells becomes a coarse grid, a primal coarse grid at the higher coarsening level. Now, there are a bunch of new keywords that I'm going to explain to you. The first one is the coarsening criterion, which means that the ADM works on the mapping of the dynamic grid resolution between the finer grids, finer resolutions, and coarser resolution at every time step based on the spatial gradient, df dx. You may also have df dt, which is the temporal gradient. But for now we are not using that, so we're going to keep it at df dx. What is the f, or the variable that we consider, is mentioned here, S1, which is the saturation of the first phase. In our example, water. That means that at every time step, the saturation of all the cells are checked and compared to their neighboring cells. If the value, the difference between the saturation of those cells, every cell compared to its neighbor, is more than 0.1, this is the tolerance, more than 0.1, it goes to a finer resolution. If it's less than 0.1, then it's okay, and it keeps it at a coarser resolution. This is the definition or the explanation behind these three keywords. Now, for pressure interpolator, we use multiscale basis function. In case of having fractures, we consider coupled basis functions, that the influence of the fractures are seen in the basis functions of the reservoir, or as the way we call it, matrix, and the influence of the matrix or reservoir is seen in the basis functions of the fracture. Now we have two extra keywords. These are just for the sake of calculations of the basis functions in order to prevent inconsistencies in the multiscale calculations and prevent having peaks in our pressure approximation. We set two limits. We set the basis function max contrast in the heterogeneity just for calculation of basis functions to be maximum 2 orders of magnitude, and the max contrast that is occurred due to the modeling of PEDFM, implementation of PEDFM for the basis function, is said to be maximum 2 orders of magnitude. We also need basis functions for our hyperbolic unknowns. So pressure is the parabolic or elliptic depending on compressibility. Elliptic or parabolic unknown. Saturation is our hyperbolic unknown. So we use constant basis functions for our hyperbolic interpolator. Now please go to MATLAB and run this simulation. Copy the full path to the directory, DARSim, ressim. The first is the full path. The second is the full name of the main simulation input file, and hit run. Now what you'll see is it's written here Algebraic Dynamic Multilevel, or ADM method, with 2 levels, 2 coarsening levels, and the tolerance for this ADM is delta S equals 0.1, which we saw in the simulator settings file. Now the prolongation and restriction operators are built. Now beginning the time dependent simulation, at every time step after creating the prolongation and the restriction operators for algebraic dynamic multilevel method, you can also see the number of active grid cells, ADM active grid cells, in this case, in this test case, and in this time step, oh, it finished. At this time step, it was 544. That means there are 544 fine grid cells used next to the coarse grid cells in this state of simulation, which is only 4.66% of all the fine scale grid cells that you may have had to use if you were running fine scale, not ADM. So this clearly shows the efficiency gain that you can have when you run ADM. At every time step, as you go forward, the number of active grid cells increases. Okay, now we want to visualize the results. Open ParaView. We want to navigate to the VTK folder. If you open the output folder that is created and then navigate to VTK folder, you see that there are 300 files. So you have the normal solution results of the simulation, the pressure, saturation, permeability, all the properties. In this file, you also have two other group of files. The first one is the ADM gridding of the first level of coarsening, the ADM gridding of the second level of coarsening. Using these files, we can see the dynamic movement of the ADM grid refinement or the ADM grid resolution as we visualize the result. Okay, I want you to open and navigate to the path of this VTK folder. I can copy the path, paste it here, navigate, and I want you to open these three groups of files. Press apply. Now deselect the first two. This is the box, which is the size of the SPE10 model, the top layer. Choose surface, permeability, column map jet, and we're scaling the column map across all the time steps. You see that the permeability is homogeneous in this example. Everywhere 10 to minus 14. I want you to choose pressure. Again, change the color map if you want to. And then rescale the column map across all the time steps. Now you see that your pressure is between 1 to 5. This is the pressure that you get at the first time step. Now I want you to change to saturation. Again, you can change the column map if you want. And this is the saturation at the first report, second report, third report. You can also navigate through the entire reports. Now, I think you can notice that there are some blocks that have same saturation. These are the coarse block. So this is your fine grid block. You can notice it. This is the coarse grid block at level 1, and these are the coarse grid block at level 2. Now, what we can do, we can also put a layer of the ADM grids on top of this. For doing that, you need to go and choose this option. So first, make sure that you are on the first one, SPE10 reservoir, and then click on threshold. Here, make sure that your scalar is active fine, not active time. So active fine. Make minimum and maximum values to be set as 1 and press apply. And then choose wireframe and then choose solid color. You can bring back the previous one, SPE10, the layer SPE10 reservoir, because it gets automatically deselected when you create a new threshold. So make it visible. Now what you see here are the fine scale grids that are used in your simulation. Now we can also put the grids for the higher coursing level as well. For that, you need to select this one. You don't have to make it visible. Select this one, click on threshold, choose active course, minimum and maximum set to be 1, press apply, wireframe, and solid color. These are the gradings of the cells that are coarse at level 1. We can follow the same procedure to make the second level grids also visible. Wireframe, solid color. Now you see which cells are at fine scale, which cells are at coarse level 1 or at coarse level 2. So if you go back from the beginning and you go to the first time step, this is what you see as the result of the first time step or report. This is actually 20 days because the entire simulation is 2000 days. So every report, 100 reports, every report will be 20 days. Second, third, fourth, fifth, and as you go forward, the ADM grid resolution at fine scale tries to capture the presence or the location of front if the gradient of your front is less than 0.1, the difference between the saturation. So at the bottom you'll see that due to due to the rarefaction of the saturation front, the sharp gradient loses its sharpness, so the difference between the neighboring cells becomes less than 0.1. Therefore, it will not keep it at fine scale, which is fine. That's what we want. We wanted it to do. This is our desired tolerance, user-defined tolerance or accuracy. So if you press play, you can see the entire front going forward, and all the fine scale grid cells try to capture wherever the saturation difference is more than 0.1. I'm sorry, more than 0.1. So again, from the beginning, this is what you see. Now, I want you to add the fractures as well. Go to the immiscible TXT domain simulation input file. At the bottom, underneath the fractured keyword in capital letters, turn this option to on instead of off. So delete on and type on in capital letters and then save. Now the simulation will run with fractures. Next time you see that there are fracture files that are red, and these are the number of elements in each fracture individually speaking, and in total you have 756 grids in your fracture network, and the rest is the same. Algebraic Dynamic Multilevel run with 2 levels, tolerance of 0.1, and then it starts solving the system. I'll pause the video. I'll be back with you when the simulation is over. Okay, now that the simulation is finished, go back to ParaView. You can remove these files. You can select all of them using your Shift button on keyboard. Press open again. Now you see many more groups of VTK files. I want you to hold your control button on your keyboard and then select reservoir, all the way scroll down, reservoir 1 level, reservoir 2 level, and then scroll up. And while you're holding the control button, choose all the fractures. We don't need the gradings in the fractures for now, just the fracture files, the solution in the fracture files. We have 30 fractures in this fracture network, that the file that you use in order to run the fracture file. In this case, there are 30 fractures defined in this system. So now I want you to choose every one of them. Fracture 15, 19, 22, 23, 24. And then press OK. Press apply. Your reservoir, you can make it surface, pressure. And the column map is already set, so you don't have to do anything with it. Deselect these two. And now I want you to select all the fractures together, all of them. Right click, add filter, common, group data sets. Press apply. Now all the fractures are linked, so you don't have to modify the configuration layout and the properties for all fractures one by one. You just choose any of these group data sets, it's fine. Use wireframe, line width, make it 5 if you want. Press enter. So now you see the thickness of the fracture. If you see that 5 is too much, you can make it 3. Maybe that's better. And then choose pressure. If you go to the first report, this is the solution of the pressure that you see. That is obtained by ADM. So this is an approximated solution for your pressure result. Now I want you to go back to the reservoir, choose saturation, also go to your group data set, choose saturation. Now this is the saturation map using ADM method at the first report. Going to the next, this is what you see for the next report, next, next, next. So what you notice is that some fractures, you can also see the movement of the saturation inside the fractures. Some of these fractures are actually flow barriers. So not only there is no saturation movement inside the fractures, they will also block the flow in the reservoir from happening. That's what you see here. So if you basically press play, you can dynamically see how the saturation moves in your system while there is this fracture network inside the domain. You can now actually go back. We want to add the ADM grid on top of the reservoir, not for fractures, only for reservoir, because that if I add the grids for fracture, it will be too much to visualize. So you go on reservoir, click on threshold, make sure that you choose active fine, press apply, both of them one, press apply, choose wireframe and solid color. You can make the SPE10 reservoir visible again. Now you can do the same for the other levels as well. Well, let us go first to the first report so you can see which cells are at fine scale, which are level 1 or level 2. So click on the threshold button, active course, 1, 1. Press apply, wireframe, solid color. Same for the second level, active course, 1, 1. Press apply, wireframe, solid color. Now this is the ADM grid lines on top of the reservoir. Now you can press play and see how the saturation is moving to the front and how the ADM gridding is following the sharp gradients in your solution. So you can see that as the saturation goes to the front, wherever you have sharp gradient, the fine scale grid cells is following it. Obviously, at some point, due to the extensiveness of the saturation front, you have a lot of fine grid cells, and you have some at coarse level 1, and you barely have any grids at the coarse level 2. But as the saturation goes to the front and the sharp gradients start to get less dominant, you also see the coarse grid cells at coursing level 2 as well. Now we want to go back and run the test cases that have the heterogeneous map of the SPE10 top layer as well. So go back to this folder, ADM two-phase flow, go to the heterogeneous folder, open immiscible txt file. That's the only file that you will have to open because the simulator settings will be identical to the simulated settings of the homogeneous test case. Now you see also the permeability file that is ready to be read. Now, the only difference is that now you are calling the permeability file with using the include keyword and the name of the file. There is one extra keyword that I put here. With this keyword, permeability contrast reduction, I am reducing the contrast of the permeability region, the heterogeneity of the permeability of this SPE10, because by default the permeability range is very intense, it's very heterogeneous, and we want to use multi-scale basis function. We can get a better result if we just smoothen it and bring the resolution, bring the heterogeneity a bit less. With this keyword, there are two sub keywords as well. This sub keyword, permeability contrast reduction, permeability contrast mean, sets the mean or the middle range of the permeability. Now we say that I want a middle range to be 10 millidarcy, and the permeability contrast order, the number that you put here, shows you how much of heterogeneity magnitude order do you want to have. That means 3 orders of magnitude. So the difference between the minimum and maximum permeability for you will be 1,000 times. So you're just reducing the heterogeneity contrast instead of maybe 7 orders of magnitude, just 3 orders of magnitude, so that we can get, in this test case, in this example, we can get a better result just for sake of better visualization. The rest of our file is the same. You don't have to do anything. Also, if you open the simulator settings, there is not much difference. Everything is the same as mentioned before. Make sure that for now the fracture file is not used. So there is this keyword underneath the keyword fracture, you have off. Now I want you to go to MATLAB and run this test case. In order to do so, make sure that you copy the full path and then go to MATLAB, DARSim, sim, put the full path in the first argument and the full name of the simulation input file here, and then press the enter. There's nothing different in this case. The only difference is that there is a permeability file that is being read. Now wait till the simulation is over. I'll get back to you. Okay, now that the simulation is done, I want you to go to your ParaView. You can use the same ParaView window. By the way, before you close everything, we put a lot of effort that we open these fractured files and all the configuration and all the settings. I want you to go back to the initial time step. This was for homogeneous test case with fractures. What we can do, we can save the state. We can save the state of all the configurations, all the files that were opened inside ParaView. This way, we don't have to do every configuration one by one again. We can use the same basically template. In order to do so, I want you to go to File and then press Save State. And what you can do, you can navigate to the root of this folder, ADM two-phase flow here, copy, paste it here, and press OK. You can save it here and can be used for both homogeneous and heterogeneous fractured test cases. You can call it fractured state, whatever you want, and press OK. There will be a file with the extension of PVSM that will be saved. Later we can use this to open the files simultaneously without having to do all the configurations again. Now please select with Ctrl A all of the items in the pipeline browser and press delete, so you will delete them. I want you to navigate, we can also do it from here. I want you to navigate going up to heterogeneous folder, output, VTK, and I want you to select these 3 groups of VTK files. Press apply, choose reservoir, deselect the other 2, choose surface and permeability. Make sure that the jet is used and click on this icon to rescale the column map to the new data. You can use the log scale when mapping data to colors option, so you can see the logarithmic scale of the permeability. This is the permeability that you have, with the orders of magnitude of about 1,000 from 2 times 10 to the power of minus 16 all the way up to 2 times 10 to the power of minus 13. Now please choose pressure. Make sure that the column map is, well, I see that the column map based on the previous settings that we did on ParaView are already chosen. You don't have to do anything. You can go to the next time step. This is the pressure result that you have with the heterogeneous map without any fractures. I want you to go to saturation now and see the saturation result. This is the first time step, first report after 20 days. Now we can also add the ADM maps. So click on threshold, active fine should be chosen, 1, 1, press apply, make it wireframe, and then solid color, and reselect the SPE10 reservoir. Now click on the reservoir 1 level, threshold, active course must be chosen, and minimum max should be 1. Press apply. and then wireframe, and then solid color. Same for the second level of coarsening, solid color. Now you can see also the ADM grids on top of the reservoir. And if you press play, this is how your saturation map look like from the start till the end of the simulation. As you can see, when the saturation front passes through a region, then the sharp front or the sharp gradient does not exist, so ADM does not have to keep it at fine scale resolution, so it can scale up to the coarse level 1 and then coarse level 2. Now we want to run the heterogeneous test case with fractures. So go back to the ADM two-phase flow and then inside heterogeneous, and then go to the immiscible file, open it, scroll all the way down, and make the fractured keyword activated. So capital on and save it. Go back to MATLAB. You can basically call the same command and run it. And the fracture files are now read. I'll wait till the simulation is over and then I'll get back to you. Now the simulation is over. Go back to ParaView. I want you to delete all the files, all the items in the pipeline browser, Ctrl A, and then press delete. Now this time we want to open the fractured result. Now if you remember, there were many files that we had to open, but thanks to the template or state that we saved, we can now use it much faster. Now we want to use this state now. Right click on File, Load State. Navigate to the location where you have saved this template or state, click, and then OK. Now, choose the option Search Files under a specified directory. Now we need to give the path of the directory where those files exist. Now, previously it was at the homogeneous test case. Now we want to use the fractured test case with the heterogeneous option. Now you click on this and then output. You don't have to go inside the VTK folder, just click on it one time with your left mouse button and then click OK. If you click OK, it takes a bit of time, it lags a bit, it freezes a bit, but it takes a bit of time till it scans and loads all the files that this template needs within that folder. You press OK, you wait for it, it may take a few seconds. There you go. Now you have basically all the files as you have chosen them and you have put them inside the pipeline browser, including the templates, threshold, color bar, everything. Now you can easily choose next option. Now this is the saturation result with the heterogeneity. You can press play and navigate through it dynamically. If you're not sure if this is the fracture test case with heterogeneity, you can stop this, go back and click on your SPE 10T reservoir and choose Perm X. You see that now this was the heterogeneous test case. You can also go and see the pressure result. This is the pressure at the first report. You can also make the fractures show the pressure result. This is the pressure result of the first report, including fractures, including heterogeneity. Please have a look at the tutorials for ParaView. You can see there are many powerful filters and layouts that ParaView has and can fit to what you want to visualize from the results of your test cases. Thank you for watching the video. I'll get back to you within the next videos and more topics.